So for today, we will do the first part of the discussion for this lecture. So what we're going to do is to answer some problems that involves the use of integral tests. So recall that the series sum n equals 1 up to plus infinity an converges if its sequence of partial sums sk is convergent. Otherwise, the series diverges. So let us recall sk. This is just the sum from n equals 1 up to k a sub n. And this is just a1 plus a2 plus until you have a sub k. So this is your sk. So you collect all of this sk, k from 1 to plus infinity, and then you look at the limit of sk as k approaches infinity. If it is convergent, then the series summation n equals 1 up to plus infinity of an converges. Otherwise, if the limit of sk as k approaches infinity diverges, then the corresponding series also diverges. Okay? We also recall divergence test. So if the limit of an as n approaches infinity is not equal to 0, then the series summation of an n equals 1 to plus infinity is divergent. Okay? So divergence test. And remember, divergence test is a test for divergence. It is not a test for convergence. Okay? And now for today's topic, we recall integral tests. So we have the sum. We have the sum an to be a series with non-negative terms, meaning your an will be greater than or equal to 0. And suppose we have a function f which is continuous, okay, which is also positive for all x greater than or equal to 1, okay, meaning f of x is greater than 0 for all x greater than or equal to 1. Furthermore, the function is decreasing in the interval 1 to plus infinity. And finally, the value of the function at every integer equals the a sub n integer. Okay? So f of n equals a sub n for all n in the set of positive integer. Okay? Then the series is convergent if the improper integral of f of x dx from 1 to plus infinity is also convergent. And the series is divergent if the improper integral is divergent. Okay? So this is the integral test. So take note of these conditions. Okay? Take note of these conditions. So you can only apply the integral test if all of these conditions are satisfied. Okay? So let's work on the first problem here. We have the sum of n raised to negative 3, okay? N equals 1 up to plus infinity. So we want to know if this is convergent or divergent. Of course, you have seen this problem already. I mean, you have seen this series already and you know if it is convergent or divergent. But for the purpose of using integral test, okay, we will solve this using the integral test. So what is this? We start with the following. We let f of x equals 1 over x cubed, okay, which is continuous, which is continuous, okay, continuous on the interval 1 to plus infinity, okay, and We know that this is greater than or equal to 0 for all x on this interval. Also, let's put that also for x greater than or equal to 1, 1 over x cubed is greater than 0. Okay? And furthermore, this is decreasing. Okay? So furthermore, if we compute for the derivative of this, f prime of x, okay, f prime of x, this is what? Equal to negative 3 over x squared, correct? And this is less than 0 for x greater than or equal to 1, which means that f is decreasing. F is decreasing on that interval, on the interval 1 to plus infinity. And lastly, you have f of n, okay? This is equal to 1 over n cubed, which is precisely this guy here. So, integral test applies. So, integral test can be applied. Integral test can be used. Okay? Thus, we have the following. We want to integrate from 1 up to plus infinity f of x dx. But this is just integral from 1 to plus infinity of x raised to negative 3. Okay? Dx. And by definition, this is the limit as t approaches plus infinity of the integral from 1 to t of x raised to negative 3 dx. And what is this? So this is equal to the limit as t approaches infinity of you get the integral, that's 1 over 2x squared, negative 1 over 2x squared, correct? And then you evaluate this from 1 up to t, and this is equal to the limit as t approaches plus infinity of negative 1 over 2t squared minus negative 1 half. And as t goes to plus infinity, negative 1 over 2t squared will go to 0. And you will get positive 1 half. So meaning, this improper integral is convergent, and therefore, by the integral test, this series is convergent. So let us write that conclusion. So, this improper integral converges, okay? Therefore, or thus, the series n equals 1 up to plus infinity of n raised to negative 3 converges. Okay? So, integral test. Okay? Question? Next problem. Same. Determine whether the series is convergent or divergent. We have the series n equals 1 up to plus infinity of 2 over 5n minus 1. Okay? So in here, same process. You check all the conditions before you apply. Okay? So let f of x be equal to 1 over 5x minus 1, where here x is from, or x is greater than or equal to 1. So you can do this, check everything for on the interval 1 to plus infinity. Okay, f is positive, f is positive. Okay, you have to check this. You just substitute f of x 1 over 5x minus 1. You know that 5x minus 1 is positive when x is greater than or equal to 1 over 5. Okay, and you have x greater than 1. So it's always positive. So you have to check that. Second, decreasing. You can do the decreasing part here. So what do we get for the decreasing part? Okay. So there is a question. Why didn't we include 2 in the numerator? Oh yeah, I forgot. So I didn't see that one. But anyway, let's just put the 2 there. Thank you. Next, f is continuous. Okay, f is continuous, and of course this function here is only discontinuous when x equals 1 over 5. Okay, otherwise f is continuous. So we write that f is continuous on the interval 1 to plus infinity. And then you have to check also f is decreasing. Okay, f is decreasing on the interval 1 to plus infinity. Let me write open here, 1 to plus infinity. And then finally, the most obvious is f of n. This is equal to 1 over, or 2 over 5n minus 1 for n natural numbers. So you have to check these 4 bullets here. Okay, you have to check these 4 bullets here, and they are all straightforward. So integral test applies. Integral test applies. And therefore, we do the integral test. We look at the improper integral from 1 up to plus infinity of f of x dx. This is equal to the integral from 1 up to plus infinity of 1 over, or 2 over, why do I always write 1? So 2 over 5x minus 1 dx. And again, by definition, this is just the limit. As t approaches plus infinity, integral from 1 up to t of 2 over 5x minus 1 dx And you know that this is just ln. Okay? So that's equal to the limit as t approaches plus infinity of 2 ln absolute value of 5x minus 1 over 5 evaluated from 1 up to t. And this is equal to the limit as t approaches infinity of 2 over 5 quantity. At t, you have ln absolute value of 5t minus 1 minus at 1, you have ln of 5 minus 1, which is 4. Okay? And of course, as t approaches infinity, 5t minus 1 will go to infinity. You have ln of something going to plus infinity is also plus infinity. So this guy here is plus infinity, which means this guy here, this is divergent, and therefore this series is also divergent. Okay? So the improper integral from 1 to plus infinity of 2 over 5x minus 1 dx diverges. Okay? So the series also diverges. And from 1 up to plus infinity, 2 over 5n minus 1 also diverges. Okay? So this is an easy test, but you have to make sure that all these conditions are satisfied. Once you've checked all of them, okay, once you've checked all of them, integral test, straightforward application, and you will get the convergence or divergence of the series. Okay? Now, of course, if you apply improper integral, for example, in this previous example here, you applied improper integral on this function, and you will get some number. Okay? You will get some number 1/2. This 1/2 here, this is the area under the curve of f of x from 1 to plus infinity. Okay? This is not the actual sum of this. So take note of that. Okay? This 1/2 here, it's the improper integral from 1 to plus infinity of f of x dx. This is not the sum of the series. So we just know that this one converges, okay? But we have to find another way to find its sum, okay? So just a reminder. Question. Next problem here, determine whether the series is convergent or divergent. You have the sum n equals 1 to plus infinity of n over n squared plus 1. Okay? So, starting point, let f of x be equal to x over x squared plus 1. Okay? Number 1 here. Oh, let us put the domain. It's from, so you have x greater than or equal to 1. So first, for x greater than or equal to 1, f of x, which is equal to x over x squared plus 1, this is also greater than, oh, this is greater than 0. Okay, definitely x squared It's always positive, plus 1. It's always positive. And you are only considering x greater than or equal to 1. So the x in the numerator will be greater than or equal to 1. Therefore, positive number divided by positive number is positive. Okay? For the continuity, this function is continuous everywhere because although this is a rational function, this guy here is a rational function, the denominator is always positive. Okay? Since f is a rational function with denominator rational function with denominator x squared plus 1, which is greater than 0. Okay? F is continuous everywhere. F is continuous everywhere. Continuous everywhere. And hence on the interval 1 to plus infinity. Hence on the interval 1 to plus infinity. Okay? To show that this is a decreasing function, we consider derivatives. Okay? Now, f prime of x, let us practice this. You have low, so x squared plus 1, derivative of high, that's just 1, minus high, derivative of low, this is 2x, over low squared, x squared plus 1 squared. Okay? Then we simplify the numerator. The numerator is what? X squared plus 1 minus 2x squared. This is 1 minus x squared. 1 minus x squared over x squared plus 1 quantity squared. Okay? And for x greater than 1, x squared will be greater than 1, and therefore 1 minus x squared will be less than 0. So for x greater than 1, x squared will be greater than 1, and so 1 minus x squared will be less than 0. Correct? Thus, f prime of x is less than 0 on the interval 1 up to plus infinity. Okay? And so it is decreasing. So let me use parentheses here. Let's have the open interval. Thus, f prime of x is less than 0 on this interval, and therefore, f is decreasing on that interval. One to plus infinity. Okay? And then lastly, you have f of n. This is precisely n over n squared plus 1. So integral test applies. So integral test applies. Okay, so let's do the integral test. Now, we look at the integral from 1 up to infinity of n over n, oops, I should use x. So x over x squared plus 1 dx. And by definition, this is the limit as t approaches plus infinity, integral from 1 up to t of x over x squared plus 1 dx. And then you can use your u substitution here. You let your you let your u equals x squared plus 1, du it's 2x dx. Okay? And then what? If u or if x is equal to t, you have u equals t squared plus 1. If x is equal to 1, you have u equals 1 squared plus 1, which is equal to 2. Correct? Which means that we now have the limit as t approaches plus infinity of the integral of what do we have? From 2 to t squared plus 1 of 1 half. Okay, 1 half. And then 1 over u. 1 over u du. Correct? So you have 1 half there coming from this, and then you have your x dx. Okay? And then you have your 1 over x squared plus 1. That becomes 1 over u. So you have this. And therefore, this is just what? So evaluating, you have the limit as t approaches plus infinity of 1 half ln absolute value of u from 2 to t squared plus 1, or this is equal to the limit t approaches plus infinity of 1 half quantity ln t squared plus 1 minus ln of 2. Okay? And as t goes to plus infinity, t squared plus 1 will go to plus infinity. Ln of going to infinity is also going to infinity. So this guy here is equal to plus infinity. And therefore, this is divergent. The series here is divergent. So, improper integral x over x squared plus 1 dx is divergent. Okay, so the series is divergent. So the series n over n squared plus 1 and from 1 up to plus infinity is also divergent. Okay. Question. Next problem. So determine whether the series is convergent or divergent. So you have here square root of n plus 4 over n squared, the terms of the series. Okay? You can rewrite this into two parts, or you can decompose this into two parts, and that's easier to work on. So this guy here, you can rewrite as the series from 1 up to plus infinity of square root of n over n squared, and then plus 4 over n squared. Okay? And you simplify square root of n over n squared. This is equal to the sum from 1 up to plus infinity of 1 over n raised to 3 halves. Okay? Plus you have 4 over n squared. Okay? So in here I'm asking you to check the premise. So you do all the conditions, or you check all the conditions. If they are satisfied, check the hypothesis or hypothesis. Okay? And all those things that you need to check, they are all satisfied. You can check for this guy here, you can check also for this guy here, and then you separate them. So we will proceed with the improper integrals. Okay? So check the hypothesis, and then we will proceed now with the improper integral. We have the integral from 1 up to plus infinity that starts with n raised to negative, let's use x raised to negative 3 halves dx. So this is the limit as t approaches plus infinity, integral from 1 up to t of x raised to negative 3 halves dx. And you know, integral of x raised to negative 3 halves, that's easy to calculate. So we have the limit as t approaches plus infinity of x raised to negative 1 half divided by 1 half. So you have negative 2 here. Okay? Then you evaluate this from 1 up to t. So this guy here, it's the limit as t approaches plus infinity of negative 2 times 1 over square root of t, that's t raised to 1 half, okay? And this is negative, so it will go down. And then at 1, you have minus 1. Okay? And as t goes to plus infinity, square root of t will go to plus infinity, but we have 1 over square root of t. So this guy here will go to 0. And therefore, you will have minus 2 times negative 1. You will get positive 2. So this guy here at least is convergent, which means this series with this term, okay, with this term 1 over n cubed of n raised to 3 halves is also convergent. For the other guy, same process. You have integral from 1 up to plus infinity. In fact, maybe you could have combined them into a single integral. But anyway, you have 4 over x squared dx. This is equal to the limit as s goes to plus infinity, integral from 1 up to s. And then let me put 4 x raised to negative 2 dx. So this is equal to the limit as s goes to plus infinity of negative 4 over x, evaluated from 1 up to s, which gives us limit as s goes to plus infinity of negative 4 and then quantity. At s, you have 1 over s, and at 1, you have minus 1. And just like before, as s goes to plus infinity, 1 over s will go to 0, so this is equal to positive 4. So both improper integrals are convergent, and therefore both series are convergent, and therefore you have the convergence of this original series. Okay? So let's just write that and combine them into a single statement. Since both improper integrals converge, improper integral converge, the series is convergent, or the series also converge. Sum square root of n plus 4 divided by n squared, and from 1 up to plus infinity also converge. Okay? So again, you have to check those hypotheses before doing the improper integral. Okay? Question? Let's have the following. So you have the sum from n equals 2 to plus infinity of 1 over n ln n. So again, I'll leave you the checking part of the validity or the conditions. Okay, let's proceed with the improper integral. So check the conditions. Conditions before applying improper integral or before applying integral test. Okay. So upon checking, they are all satisfied. Take note, your n here, it starts from 2. Okay, it starts from 2. Because when n equals 1, ln of 1 is 0. So you cannot have denominator 0. Okay? And from 2 to plus infinity, ln of 2, it's positive. So this guy here, it's always positive. And then is it decreasing? Check. You can use your derivative test. Okay? You can use your derivative test to do that. Of course, continuity, I already mentioned, although we have denominator here, the denominator will not be 0. And otherwise, the rational expression here is continuous. So you have to do that and give those details, the necessary details. Okay? So we proceed with the improper integral. We have the integral from 2 to plus infinity of dx over x ln of x. And then by definition, this is the limit as t approaches plus infinity, infinity, integral from 2 up to t of dx over x ln of x. And then you can do your u substitution here. You can let u be equal to ln of x. Du is 1 over x dx, which means this guy here is just the limit as t approaches plus infinity. Let's change the limits of integration. U equals 2, or sorry, x equals 2. You will have u equals ln of 2. X equals t. U will be ln of t. Okay? So we now have limit as t approaches plus infinity of the integral from ln of 2 up to ln of t of 1 over u du. And that's an easy integral problem. So we have the limit as t approaches plus infinity of ln absolute value of u evaluated at ln of 2 up to ln of t. Okay? And therefore, we have the limit as t approaches plus infinity of ln of absolute value of ln of t minus ln of the absolute value of ln of 2. Okay? But as t approaches plus infinity, ln of t will go to plus infinity, and therefore ln of something going to plus infinity will also be plus infinity. So this guy here will be plus infinity. Okay? Which means this is divergent. Okay? Question? So let's have the next problem here. Let's see. Explain why the integral test can't be used to determine whether this guy here converges or diverges. Oh, I forgot to write something here. So explain why the integral test can't be used to determine whether this guy here converges or diverges. Let me add that. Converges or diverges. Okay? So what do you think is the reason? So since cosine pi n, this is either 1 or negative 1. It is 1 when n is even. When n is even. And it is negative 1 when n is odd. Okay, when n is odd. Okay. The function, if we consider the function f of x equals cosine pi x, over square root of x, okay, will not remain positive, will not remain positive okay, on an interval interval, say, let us write the interval, let's use r to plus infinity for any r, for any r. So the function f of x equals cosine phi x over square root of x will not remain positive on an interval r to plus infinity for any r. For any r greater than 1. Which means even at a, even if you cut the interval for your integral test, okay, even if you cut it, you will not get a positive function. Okay, so from 1 to plus infinity, you can do 10 to plus infinity, or 100 to plus infinity, or 1 million to plus infinity. So whatever interval you use, this function will never remain positive. So you cannot use integral test. Okay, so integral test cannot be applied. Integral test cannot be applied. Okay, question. Okay, so for my last problem for today, so find the values of P, okay, for which this guy here is convergent. So we saw earlier in a previous example, we had P equals 1. So the question is, when is this actually convergent? Or can we find a value for P that this guy here is convergent? So check all the conditions for integral test. So check the hypothesis. So hypothesis for the integral test. And then it can be applied. I mean, this integral test can be applied. So we do that. So we start with the function f of x equals 1 over x ln of x to the p. Okay? Of course, here x greater than or equal to 2. And then you check the conditions, and then integral test can be applied. So let's look at the improper integral from 2 to plus infinity of 1 over x ln of x to the p dx. And by definition again, you have the limit as t approaches plus infinity, integral from 2 to t of dx over x ln of x to the p. And same substitution as in before, you have u equals ln of x, du equals 1 over x dx. Okay? And then this guy here now becomes the limit as t approaches plus infinity of the integral from 2 to t of dx of, du over u to the p. Okay? But this guy here, let's just write this as integral from 2, sorry, it's not 2, it should be ln of 2, okay? ln of 2 to ln of t. So ln of 2 to ln of t, ln of t. But this guy here, okay, by definition, we bring back the improper integral. So this is the integral from ln of 2 to plus infinity of du over u to the p. And then you apply your p-test for the improper integral. You know that this is convergent when p greater than 1 and divergent when p less than or equal to 1. So using p-test for improper integrals, using p-test, okay? The improper integral ln of 2 to positive infinity of du over u to the p is convergent for p greater than 1 or convergent, yeah, when p greater than 1 and divergent when p less than or equal to 1 and divergent when p less than or equal to 1. Therefore, this series here is convergent when p greater than 1 and divergent when p less than or equal to 1. So it is consistent with the previous example. We had p equals 1 and we saw it was divergent. Okay? So, question. Okay? So, that's my last example for today. And thank you for staying and have a good night.